Okay, so we're starting chapter 15 now, and 15 we're going to be dealing with integration with multivariable functions. Now, I think the best place to start when thinking about what integration should look like for a multivariable function, in particular a function of two variables for now, is to review the definite integral for a single variable function, because we're going to try and use that as a model for what we do in chapter 15. So going back to how we define the definite integral all the way back in calculus 1, really, is we start with a function of a single variable, f of x, and for the sake of this discussion, we're going to assume it's continuous, and the goal here is to try and find the area under that curve on some closed interval a, b here. And the trick that we used in calculus 1 is we took the interval a, b, broke it up into these little subintervals, all of equal width. That width we refer to as delta x. And the end points of those subintervals we enumerate. We call them x1, x2, x3, so on and so forth. That creates the base of each one of these little rectangles that we're going to use for an approximation. The height of each of these blue rectangles comes from selecting a sample point in each of those subintervals, which is then plugged into our function f of x, giving us the height of each rectangle. Those sample points, if we're using a manual calculation, can be chosen intentionally. So we can choose, for example, to use left endpoints for each rectangle to plug that in and get the height of each of those rectangles. We can use right endpoints as well. We also talk about the midpoint rule, which says that if we use the midpoint of each subinterval as our sample point, that gets us a good approximation for the area under this curve. But there's really no rule that says we have to choose one way or the other. We can choose them randomly if we want to. Each of those sample points we refer to as xi star, where I refers to which subinterval we're talking about. Okay. After creating an approximation this way, we add up the areas of all of those rectangles. That's an approximation for the area under the curve. And as you know, if you take the limit as the number of rectangles that we use goes to infinity, so the limit is n goes to infinity, that approximation becomes accurate, and we call that the integral, the definite integral of f of x from a to b. So this is all review, obviously, but how do we take this idea and bring things up one dimension to talk about integration with functions of two variables? So down a little bit. The difference here is that if we talk about a function of two variables, we're no longer talking about a curve, we're talking about a surface. And so it makes more sense not to talk about the area under a surface, but the volume under a surface. So here, this blue surface is given by the function z equals f of xy. And if we project it into the xy plane, we have this yellow rectangle, which I'm calling r. So for section 15.1, we're going to be strictly looking at just rectangles down here. I want to come up with a way of determining the volume of the solid containing all points beneath this surface, this blue surface, and above this rectangle r. So the solid that you can kind of picture being the volume under that surface. Now there's some notation introduced here. So the rectangle here in the xy plane is determined by two intervals, one on the x-axis, one on the y-axis. So the interval AB on the x-axis, the interval CD on the y-axis gives us this rectangle. We use this notation to denote that rectangle, AB cross CD. That's not a cross product. That's something in set theory we call a Cartesian product. And basically it's just a way of constructing ordered pairs out of two sets. So this set represents the set of all ordered pairs where the x-coordinate is somewhere in this interval and the y-coordinate is somewhere in that interval. The set of all such points creates this rectangle. Okay? So using the Riemann sum idea from calculus 1 as a guide, what we'd like to do is approximate this volume using solids that are whose volumes are easily computed. And the solids that we're going to want to use are rectangular prisms or rectangular boxes. And we construct those. Let's move this up a little bit. This yellow rectangle in the xy plane is shown here, but the intervals AB and CD that we're using to define that rectangle on the x and y axis can be individually broken up into subintervals, much in the same way we do with definite integrals of a single variable. If I divide the interval AB up into these little subintervals, and if I divide the interval CD up into its own subintervals, it creates this grid of subrectangles in our rectangle R. Now the notation I'm going to use for this, the number of subintervals I break A, B into is going to be M, and the number of subintervals I break C, D into is going to be N, giving me a total of M times N little subrectangles here. And the subrectangle coming from the ith subinterval here and the jth subinterval here, I'm going to call Rij. And we can use, again, that cross notation to denote it. Now, each of these subrectangles, let me scroll up a little bit. So here's this, this grid, but now in 3 dimensions. So the grid lives in the xy plane. And notice the surface that we're looking for the volume beneath is above that rectangle. What we want to do is in each of these subrectangles choose a sample point. Same idea as what we did in definite integrals in Calculus 1. There's no necessary requirement for how we choose it, but we just choose one sample point in each subrectangle. That sample point is going to get plugged into your function f of xy, and that's going to determine the height of this rectangular box right here. Okay. For any one of these rectangular boxes, the volume is going to be the area of the base, which is a rectangle, times the height. So that means that for each box, we can compute its volume as f of xij star, yij star. This represents the sample point that was chosen, plugged into our function, giving us the height, times delta A. Delta A is what we're going to use to represent the size of each subrectangle. We're specifically choosing these so that all the subrectangles have the same area. If we were to add up all of those little all of the volumes that we get from each subrectangle in the box that they create, which you can kind of see here, we get something that approximates the volume under the original solid. Okay, and as you would expect from Calculus 1 and the definite integral, if we take the limit as the number of these boxes goes to infinity, that volume should become accurate. So still working with the approximation though, this little relationship describes that approximation. V, my volume, is approximately the double sum of f of xij star, yij star times delta A. Again, that's just adding up each of these boxes. Now, you may not have encountered this double sum thing before, so I want to illustrate how we compute double sums with an example.